Welcome. Let's go over what writing a good lab report looks like. I graded your lab reports pretty hard on purpose, not because you guys didn't do a good job, but because I'd like you to see how far you can go with this, and you now have the opportunity to make corrections. So what should a good lab report look like? Your title. I got all kinds of things for titles with our Oreo Cookie Lab, including questions and some cute descriptions. However, there is one acceptable format for the title of any scientific research that you're reporting on. All lab reports, whether you're at a college, a university, here at the high school, or even a research company, if you plan to share your results in the format of a lab report, your title must look like this. And you literally write the effect of the independent variable, whatever that may be, on the dependent variable, whatever that may be. So, effect of type of Oreo cookie is my independent variable on the dependent variable, mass of the filling. And that's it. It's very formulaic, and it's that way on purpose because the goal of scientists reading your lab report is to get the most information they can in the shortest amount of time. This title and this format, used universally around the world, tells researchers immediately what your entire lab report is about. And that's important. If you're doing an observational report, which this would be surveys, so if you're surveying people's opinions on the current crisis in Syria, then you would have more descriptive title. But otherwise, if you have an independent variable and a dependent variable, this is the format of your title. Your purpose section. This should be no more than 2 sentences. The first sentence is what you are doing. We hope to answer the question, are double-stuffed Oreos really double-stuffed? Period. Then you include your hypothesis. And for our purposes, your hypothesis will be in an if-then statement. So the if describes what you will measure. In this case, if the mass of the Oreo filling in regular and double-stuffed Oreos is found. Okay, so we know what we're measuring. Then, what do you expect to see? Then, double-stuffed Oreos will have twice the amount of filling. Period. That's it. So the hypothesis here is that the group thinks that double-stuffed Oreos will have twice the amount of filling than the regular stuffed Oreos. Your materials and equipment. Concise description of the materials. You do not need to list how you're going to use these materials because that will come later in your procedure. And again, scientists are all about keeping it short and not being very repetitive. So in this case, just list them. This can be in one sentence if it's a short lab, like our Oreo Cookie Lab, where there's not a lot of instruments involved. If there are a lot of materials and a lot of equipment involved, you may break it up into 2 sentences. One, our materials are, and then the second sentence, the equipment we used, and then just list them. Just a comma list with a period at the end is fine. Your procedure. Some of these were great, and some of them didn't give enough detail. This is a step-by-step description. So another researcher, or in your case another student, should be able to read your procedure and tell exactly what you did. If it helps to think of it like describing a movie in your head, based on your description, someone should be able to kind of see a movie in their head of what you did. You don't have to say, we gently twisted to remove the cookie from the cream. You don't have to include a lot of descriptors, and you don't have to make it fluffy and sound good. It just has to be complete. Again, Scientists want it short and sweet. Don't want a lot of fluff, don't need a lot of description, but it does need to be detailed enough that someone else could repeat it. The other thing to remember is that you are telling your reader what you did. So use the past tense and keep it in paragraph form. Data tables. Data tables are actually kind of difficult to come up with. You need to think about this and put some thought into it. A lot of times the thought, almost always, the thought on what sort of data table you're going to have should come at the beginning of your experiment. Oftentimes, if I give you the experiment, I will give you the data tables as well. But when you're designing an experiment of your own, you need to make sure your data table is as complete as possible. And that takes some effort and it takes some time. And you may have to rearrange things. Do I want the mass of the wafer and the filling on the left-hand side and the Oreos across the top? What would look better? What would make sense? So you may actually have to spend some time creating a data table that looks nice. Also, don't forget to include any units that you used. In the Oreo Cookie Lab, you were measuring the mass in grams, so make sure that's included. Overall, though, your data tables were all right. Calculations. Show any calculations used in interpreting the results. Some of you listed your actual calculations with your numbers in them, and that's fine and that's appropriate. If you'd like to do something like this, you may, where you just describe what you did. Some of you stopped at this first sentence, though. We calculated the average mass of the filling for the regular and double-stuffed Oreos by adding the mass of the filling for each type of cookie and dividing by 4. Well, you actually did a little more calculation than that, especially if you compared the mass of the icing or the filling in the regular Oreo and the filling in the double-stuffed Oreo. Those comparisons are probably math that you did in your head. You probably didn't write it down, but you still did it in your head. You need to show how you used that data and what did you do with it after you found the averages. How did you compare them? So be careful to explain the second part too. Then we compared the mass of the fillings by creating a ratio of regular to double stuffed and reducing it to determine if it was a 1-to-2 ratio. So it tells the reader how you used those averages, because you did compare them, even if you compared them in your head, to determine whether or not your hypothesis was supported or rejected. So remember to include that here in the calculations. Graphs. Some of you just completely skipped this part. Perhaps you didn't understand that you needed to create a graph. Be careful with graphs. A couple of notes here. In my sample graph, the independent variable is always on the x-axis. Some of you were tempted to turn this graph and have the bars coming out from left to right. I'm not sure. I know some of the programs like Word and Excel will make these kinds of graphs for you, but this is not appropriate in a scientific paper. The independent variable always needs to be on the bottom, and your dependent variable needs to be on the y-axis. And make sure you include units and labels. Excuse me. So in your Oreo Cookie Lab, you would have 2 bars, one for regular Oreo filling and one for the mass of the double-stuffed Oreo filling. And you only need to include the averages. The graph is sort of a quick visual that someone who's reading your paper can flip through to see the answer to your question or your title, the effect of the type of cookie on the filling, on the mass of the filling. They can flip to this chart and see regular cookie here, double stuffed cookie here, and the mass of the filling. If you start to include, if you found the mass for 4 regular cookies and 4 double stuffed cookies, and you put those on here, that's 8 lines, and then you add another one to do the averages, that's 10 lines. It gets really confusing. So really keep the graph as simple and straight to the point as possible. So just graph your average data. Data trends. So what does your data tell you? When you look at that graph, trends are things that you see visually. So this right here, this peak in July and August would be a trend. Okay, this shape, if you are familiar with this shape, it's the parabola. It goes up and down. So that's what we're talking about with trends. After you make your graph, take a look at it, and the trend, the temperature rises from February all the way until July and August, and then the temperature drops again until February, and then it rises again. So that would be the trend. It's just a simple statement about what your graph shows you. Errors. You guys did pretty good on this part for it being your first time. You need to add a little bit more depth though, and many of you forgot this last part and what steps were taken to minimize their effect. These are errors that could have occurred while you were doing the experiment, not hypothetical if someone out in outer space were doing this experiment, but what you could have experienced. So take a moment, pause it, and read over this. I hope you noticed when you read through it that you could talk about the scale, which many of you did, but you need to talk about why it wasn't doing what you wanted it to do or how it didn't do what you wanted it to do. You need to be very specific. So if you want to mention the scale, you should say something like, our scale was only accurate to 1/10 of a gram. This was unavoidable, but may have resulted in mathematical error. So there, you've said your piece about the scale, that it only measured to 1/10 of a gram. Another unavoidable error that you had was your sample size. You were only given 4 types of each cookie to work with. If your sample size is small, and by small I mean anything less than 50, so 50 trials or 50 things, in this case 50 regular cookies and 50 double stuffed cookies, if your sample size is small, you need to explain why it was small. Okay? So in this case, the why is because it was unavoidable. That was all you were given. To minimize this error, which having a small sample size is a mathematical error, to minimize this error we could have compared results to another group or combined our resources. Another source of error was the consistency of the filling. It kept sticking to the knife and the scale. So by consistency I mean the gooiness of the filling. And a lot of you mentioned that it does stick. And some of you listed about the filling being sticky on the knife and the scale. We tried to minimize error here and then explain that you wiped the knife carefully, or you zeroed the scale out to get rid of crumbs. What did you do to try and make your data even more accurate? Your conclusion. These were, for the most part, these were good. A couple of little notes. Remember, you can't prove anything with only one experiment. So, in this case, you cannot use the word prove. You just can't do it. You need to get in the habit of saying that the data supported or did not support your hypothesis. But your data, it's just too small a sample size to prove anything. And that's extremely important. Another mistake that I saw with the conclusion is that you listed all of these possible errors, how, the scale and the filling was sticky and the crumbs of the cookie and all of these things. And then when your data said that the double stuffed were only like 1/10 of a gram away from actually being double stuffed, you were like, oh yeah, they're not double stuffed. But if you stop and think about it, and you consider some of the possible errors in the experiment, the small sample size, then there's really the only valid conclusion at that point is that you need more testing. And that's okay. It's okay to say that we're not sure whether our data supports or doesn't support our hypothesis because we had a small sample size. These were possible errors, and there's no way to determine whether our hypothesis is supported or not. Further testing is needed. That's an acceptable and a very well thought out conclusion. It shows that you understand that just because your 4 cookies said that the double stuffed Oreo wasn't double stuffed by 2/10 of a gram. I mean, come on, 2/10 of a gram? Really? That's not very much, right? I mean, a paper clip is 1 gram. So 2/10 of a gram is very, very small. And I know from watching, a lot of your filling, some of it was left on the cookie, some of it was on the scale. So to say with any certainty, one way or the other, is a little dangerous at this point. Now, on the other hand, if you want to say the data that we have supported our hypothesis, and here it is, always list your data, kind of like supporting your conclusion, like actually list out and show the data that you're talking about so that the reader can see it too. Don't make them hunt back through your paper for it. So you give your data, you say, according to our experiment, although it was flawed, we conclude that even though the double stuffed cookie was off by 2/10 of a gram, we feel that may be close enough that our hypothesis may be supported. However, there's not enough to say for certain. Further study is needed. That's always appropriate. We'll be talking more about what does your data really say as we go throughout the year. Further investigation. I didn't realize this one would be so confusing for people. So, and I would say over half of you made this mistake, probably around 80%. Further investigation was not necessarily how you would make your experiment better, but what could you do now? What could you do as a result of doing this? What other questions might be interesting and related to what you've done? So one of the thoughtful ones that I had was perhaps they measured the mass of the filling this time, but a further investigation may be to measure the density of the filling, or the consistency or the chemical makeup of the filling to see if it's actually the same. Because if it isn't the same, then can you really compare their masses? So it's another investigation, something a little bit deeper, a little bit further, an extension of this laboratory activity. And that's the last section. If you have questions writing your lab reports, please email me, and good luck revising these and get them turned in soon.